All right, looks like we are live, and I want to welcome everybody to Standing for Truth. My name is Donny, and I am your host for today's program on the Missoula Flood and Flood Geology. I also have Matt with me as my co-host for today's exciting program. As always, it is a privilege to have Michael J. Oard back as a speaker for this important topic. This is Mike's 11th time on the program. He has been a huge blessing to this ministry. Mike will be giving specifically a presentation. Then we will enter into a discussion and also audience question and answer period. Therefore, if you do have questions for Mike, please make sure to send them in by tagging me in the live chat. You can tag me either at Donny or at Standing for Truth. Now, before I hand it over to Mike, I am going to hand it over to Matt for a formal introduction into our guest. Firstly, I do want to remind everybody that for links to all of Mike's past presentations he has done with us, those presentations range from the receding floodwaters, the Ice Age, answering challenges and refuting objections, the Green River Formation, flood boundaries, and more. Please do check the description box where those are linked for everybody to see. Okay, so Matt, thank you firstly for co-hosting this program, brother. And I'm going to hand it over to you to give Mike a proper introduction.
Will do. Hopefully you can hear me good.
Yes.
Yeah, Michael has a master's science degree in atmospheric science from the University of Washington and is now retired after working as a meteorologist with the United States National Weather Service for over 30 years. He has researched and speaks on the compelling evidence of Noah's flood and the ice age that followed, and how the incredible woolly mammoth connects to biblical history. Michael has published many papers in the field in widely recognized journals and has written An Ice Age Caused by Genesis Flood, Ancient Ice Ages and Gigantic Submarine Landslides, the Missoula Flood Controversy, including the Genesis Flood and the Frozen Record. He has also authored Frozen in Time, The Weather Book, and Life in the Great Ice Age. Yeah, that's right. I hope I got all those right. So many books.
You did good, Matt. And I've got about 90% of them behind me, including Mike, your newest one. Excellent work on this. This has been really helpful. Biblical Geology 101. Written with Dr. Rob Carter, another one of our favorite young earth creationist scientists. So, yeah, Mike, again, I know how busy you are. You've been extremely busy doing ministry work over the summer. And so we greatly appreciate the time that you give us for these shows. Mike, how you doing and how have you been over the summer?
It went fast and it was good. It was good.
Good to hear. And I know the International Conference on Creationism took place as well. So I'm sure we'll have lots to discuss in the Q&A period, as we do have lots of young earth creationists in the live chat. And so again, please, if you have questions, criticisms, challenges, whatever they may be, make sure you're tagging me and we'll do our best to engage them. Mike, we're going to hand it over to you now. And whenever you're ready, we can get into your presentation.
Okay. You see it just fine?
Yes, looks great.
Okay.
Actually, Mike, maybe one recommendation, sorry. At the bottom, the rectangular box, if you click hide, then it'll remove the box from the screen and it won't block some of the text. Yes.
Yeah, good idea. Well, this topic is not just about a nice flood in the Northwest states where I live. I'm from Washington State originally, but it has some things to tell us, teach us about the Genesis flood, about how secular scientists will view evidence for the Genesis flood, which I believe is abundant out there. Anyway, I'll get started. Here's an overview. What is the Lake Missoula flood? I'll explain that because I'm sure many in the audience ever heard of it. Even many people in the Northwest states never heard of it. So I'll get into it. And a question, was there more than one Lake Missoula flood? And I'm going to make two major points from all this. Secular scientists are blinded against catastrophic processes. That's one lesson we learned from the Lake Missoula Flood Controversy. And it can be used as an analog for certain features of Noah's flood, mainly the runoff of the Genesis flood, because the Lake Missoula flood was, once it broke, it was a runoff event. And it left certain telltale features on the surface that are similar to other features seen on the surface of the continents globally, thousands of features. Anyway, let's get started. What is the Lake Missoula flood? Well, a good description of it was during the peak of the Ice Age, a finger of the Cordilleran ice sheet, right there in northern Idaho. Can you see my cursor?
Let me see. Yes, yeah, I can see it.
Okay, northern Idaho, it blocked the Clark Fork River and ponded this water in the valleys of western Montana. At the boundary of Idaho and Montana, it was 2,000 feet deep. Over the city of Missoula, it was 1,000 feet deep. And it broke through the ice dam and filled up Glacial Lake Columbia, which was an ice dam on the Columbia River that had a lake clear up to Spokane, Washington. You see it there. Then it broke and overtopped a ridge to the southwest and flowed down that green area, eroding the brown colors, which are silt. There's about 100 feet of Palouse silt that secular scientists think is loess, which I think only the top of it is, but I'm going to revisit that probably after the presentation. And it carved up 50 cubic miles of basalt. The basalt is the green area and the soft silt, and spread south, and couldn't get through a narrow gap and formed an instant lake 600 feet deep around Pasco, Washington, spread into the Hermiston, Oregon area, and down the Columbia River through the Columbia Gorge, following my cursor, backwashed up the Willamette Valley, clear to Eugene, before it emptied out into the Pacific Ocean. So that's the Lake Missoula flood at the peak of the Ice Age. We know it's at the peak because in order to have a lake 2,000 feet deep, you had to have ice probably about 2,500 feet thick, which is about what it was, because the mountains to the east and west, which I'm pointing to in my cursor, were unglaciated at the top. This was a lobe filling up where Lake Pend Oreille in northern Idaho is located. Oops, I mean over here. Yeah. So that's the Lake Missoula flood, and it broke and emptied out in about 2 days and spread through eastern Washington in about maybe a week. Here's a little closer of it, you can see with the ice. Now, there's a few creationists that think that the features of the Lake Missoula flood can be explained by the Genesis flood. But I'm going to point out some features that indicate that can't be the case at all. But anyway, as I go. Anyway, here's a blow up of that same kiosk. That kiosk is found on the northern shore of Lake Pend Oreille off the main highway that goes through, I think, Highway 2. Anyway, just east of the ice dam, the ice moved east up the Clark Fork River Valley. Excuse me. And it forms grooves and striations along a cliff. Along the road, you can see just as the ice spread east up the Clark Fork Valley. This is Vern Bissell from Portland, Oregon, for scale. Anyway, J. Harlan Bretz was the one who discovered this. Great detective work. He started in 1923 and wrote many papers on the subject, many aspects of it, in the Journal Geology and the Geological Society of America Bulletin. So he discovered a lot of weird features in eastern Washington. For instance, dry falls. This looks like a huge waterfall with a plunge pool. By the way, that's about 125 feet deep. Another plunge pool here and down over here. If this was erosion over millions of years, you wouldn't have sharp edges like this. It erode those edges, and it'd be just a gradual descent down to this area here. But it's just left like that. So based on this and other features, he proclaimed that there was a monstrous flood through eastern Washington. He had a problem, though. He didn't know where the water came from, and that didn't help his case. But anyway, some of the other features, well, this is a feature of dry falls here, which you only saw part of it. It's about 4 miles long. And by the way, it left an erosional remnant in the middle called Umatilla Rock. I'll speak more about erosional remnants later on in the presentation. And then here's another set of plunge pool with a frozen waterfall right here. This is west of Quincy, Washington, where the water flooded the Quincy Basin south of at Euphrates southward, about 200 square mile gravel bar, and it overtopped a ridge, north-south ridge, just west of the Columbia River, and it overtopped and eroded that ridge back as a retreating waterfall. And this is one of those retreating waterfalls. It's got several names. Ancient Lakes is one of them. Can't think of the other ones, but anyway, there's a series of other plunge pools to the right of this photo, but here's the last ones right in here. They're green because of the algae. Now, I don't take people, I have guided people through eastern Washington, but I don't take them here because you're on top of a cliff, there's rattlesnakes, and there's nettles, so and probably ticks. So I just don't take people there. And we see all these gravel bars, sometimes out in the middle of nowhere, like this one southwest of Spokane, Washington. That's my wife for scale to the right. You know, we on our way to Washington from Montana, we'd stop at some really exotic scenic areas like gravel bars and gravel pits. And of course, my children objected like crazy at the time. But anyway, I visited a number of these. Here's another gravel bar. And this is west of a ridge south of Arlington, Oregon. It's off the top of a ridge. You can see the delta features from the water moving from east to west over that ridge. Arlington, Oregon is in the Columbia River Gorge. The water was 1,000 feet deep going through the Columbia Gorge. And I might add, it went over Spokane, Washington. The current location of Spokane, Washington, 600 feet deep, and was going anywhere from 60 to 80 miles an hour in places. And it spread over Portland, Vancouver area, 400 feet deep. Yeah, quite an impressive flood, wouldn't you say? And here's another gravel bar. This is northeast of Yakima, Washington. The Columbia River is down in this area right in here. These are the Saddle Mountains, one of those east-west lava ridges in that area, buckled up due to north-south compression. And here's a gravel bar right here. It's about 100 feet tall, and it's 15 miles long, and it came from the Saddle Mountain Water Gap 15 miles away. There's a road that drives you all around here. So I've seen it. I saw it just about a week ago, as a matter of fact, when I left Yakima. We go by this. Very impressive. And here's a gravel bar in Montana. It's about 200 feet thick, where the water eroded the belt supergroup rocks, forming, I think, Rainbow Lake. And as it scoured out that area, it dumped the gravel just to the southwest of those lakes. And it formed a huge gravel bar in the Vancouver, Portland area called the Portland Delta. It's about, it once was filled in where the Columbia River now lies. It's about 200 square miles in area, and it's 300 feet deep. And this gravel sometimes is huge boulders, indicating the powerful flood going down the Columbia Gorge to the right at up to 1,000 feet deep. We know it's that deep because of scour features and also erratic boulders from northeast of Grand Coulee, or I should say from the Okanagan area and maybe British Columbia. Anyway, that are spread, are found above the current river. And speaking of erratic boulders that were transported, here's a boulder of basalt lava. It was eroded when the flow through the Grand Coulee was moving 60 miles an hour and formed a huge gravel bar, like I said, at Ephrata and southward, what's they call the Quincy Basin. And this has been transported about 5 miles. So, and all around here, there's a lot of granite erratic boulders. And here's one of those granite erratic boulders in the Columbia Gorge, about 400 to 500 feet above the river. The only way it can get down here is by floating in icebergs. And here's a granite erratic on the ridge south of Arlington, Oregon. Arlington, Oregon's right in the Columbia Gorge. And so this is probably one of the biggest granite erratics I've seen. And that didn't roll down, by the way, especially when it's on a ridge. It had to be transported in an iceberg. And here's a fantastic erratic boulder. This is southwest of, about 50 miles southwest of Portland, Oregon. This is a metamorphic shale. You can see the shale texture of it. It's called argillite. No argillite outcrops in the whole state of Oregon. So what's it doing down here, southwest of Portland, Oregon, right in the low areas of the Willamette Valley, as you see in the background? Well, the only way you can get down is by an iceberg. Now, this is some powerful evidence that these features are not from the Genesis flood, because the Genesis flood would have to roll this down. And as you see, it's a shale, a little harder. It wouldn't last more than a mile. They couldn't make it down this far, transported probably 500 miles from where glacial Lake Missoula was located. This type of rock is very common in the belt supergroup, which outcrops from near Bozeman, Montana to Spokane, Washington. It's over 20 kilometers thick of mostly quartzite and argillite. Quartzite's a metamorphic sandstone. So there's a lot of things in this area that give you a lot of information about not only the Lake Missoula flood, but also the Genesis flood. And here's a plot. This is an old plot, I think from 1935, of all the granite. I think these are granite erratics in the Willamette Valley that have been found clear to Eugene. And the only way they're going to get, some of these are pretty good sized granite boulders. And the only way they're going to get down here is coming through the Columbia Gorge and backwashing up the Willamette River to Eugene, and the icebergs get stalled on the land as the water starts draining out of the Willamette Valley towards the Pacific Ocean. And on the path of the flood, remember, it's you have the Columbia River basalts cover most of eastern Washington. On top, you have about 100 feet of silt called the Palouse loess. I don't think it's a loess, mainly because you have marine sponge spicules in it, probably marine, common, not unusual in this. And of course, but the top of it's been blown around during the Ice Age, so it's technically the top meter or so is a loess, true loess. Anyway, these are streamlined hills. There are hundreds of these along the path of the Lake Missoula flood. Streamline was the water goes along, it streamlines it. This is also some evidence that there was only one flood, because if there were multiple floods, it would have planed all these things out, and you'd just be left with basalt. Here's some more pictures of those streamlined silt hills. And it carved up eastern Washington, forming what's called coulees. That's the local vernacular, standing for vertically walled canyons and flat bottomed that are flat bottoms. Now, this is the famous Grand Coulee, the largest coulee by far, but there's other coulees. And it's cut in the basalt, 900 feet thick basalt on both sides, about 6 miles wide at the widest and 50 miles long, carved up in a matter of days in the Lake Missoula flood. Now that's pretty powerful catastrophism, all post-flood at the peak of the Ice Age. Here you see in the background an erosional remnant called Steamboat Rock. And that's one of significant erosional remnants left from the Lake Missoula flood. And I'll talk more about that later. Here's looking down from Dry Falls to the south in the lower Grand Coulee, which is loaded with a lot of lakes. Great water activity there, but it's really hot in the summer. You might notice that on the right side, the basalt is higher than on the left side. That's because you had a bending in the basalt down to the east like this. It's called the coulee monocline. And when it bends like that, it cracks and stretches, and that was a weak area that the flood took advantage of to form the lower Grand Coulee in a matter of a day or two. Pretty fantastic. And as evidence for the glacial Lake Missoula, there's shorelines all over where these valleys are. I've seen them in numerous locations. One of them most famous is Sentinel Hill. This is from out from the University of Montana in Missoula. I'm looking east. M stands for the University of Montana. And you can see these nice shorelines, strand lines left. And I believe they represent yearly fillings of glacial Lake Missoula. There's another mountain to the left that you can't see that I've actually climbed up. Actually, I've climbed up to the M here too. And the vertical distance between these shorelines is about 30 to 40 feet. So you're adding water at the peak of the Ice Age. You were having an equilibrium from the addition of snow and ice to the melting. And so each summer, you'd melt a lot, up to filling this up 30 to 40 feet a summer. And it rises. As it rises, it protects the shorelines below it. So that's how I believe they formed by rising water, because you got to protect this pattern. And once they're underwater, they're protected. Now, these shorelines are in both hard rocks of the belt supergroup and also in soft clays and other soft rocks in the Missoula Valley. So indicating that the Lake Missoula flood didn't occur that long ago. And if you go north of Missoula, you see the Camas Prairie, very famous, especially seen by this aerial photography of these ridges, which they never really knew what they were till aerial photography. The ripple marks, about 50 feet tall of gravel. And it's this pretty steep slope going down to the south. What you have is up here in the background, the Little Bitterroot Valley, which you find shorelines etched all over the place, I might add. And it overtopped a ridge about 400 feet above this valley. And the water above this ridge was probably about 800 feet higher. So as the Lake Missoula flood emptied out, it crossed this ridge and was moving, they estimate, 60 miles an hour down this slope, creating these gravel ripples. And a lot of gravel bars in northern Idaho and eastern Washington. I think about 100 of them have ripple marks on top of them. This one's in northern Idaho. And from space, you can see the path of the Lake Missoula flood as it overtopped a ridge, which is approximately in this area right in here. There's generally two paths, the Cheney-Palouse path down this way, and the one that went through Grand Coulee and also Moses Coulee, which I believe is right over here, and converged down this way. But anyway, this is a drainage pattern 100 miles wide. And this light color is the silt that's still left. It left. So, Lake Missoula flood was a monstrous flood. Maybe not the second largest in the world, the Genesis flood being the largest by probably 10,000 times. But it gives you an idea of what could happen in a global flood. But since the discovery of the Lake Missoula flood, Victor Baker, secular geologist, has discovered about 40 other ice age floods around the world. One possibly as large as the Lake Missoula flood, but otherwise they're generally smaller than the Lake Missoula flood. And this one that is on par with the Lake Missoula flood occurred from the Central Asian mountains going north into Siberia. Okay, how many Lake Missoula floods were there? Well, Bretz, who quit publishing on it about 1933 with a monograph on the Grand Coulee, believe there's only one flood, but they discovered that an ash layer at the top of some Rhythmites in the Wallula and Yakima River valleys, the ash is from an eruption of Mount St. Helens. So Richard Waite in the 1980s said it's very improbable for an eruption of Mount St. Helens to occur at the same time as one glacial Lake Missoula flood. Therefore, he came to the conclusion that each of these Rhythmites, which I'll show you, represents a separate flood. And based in the Walla Walla River Valley, at a place I will show you soon, he counted 40 Rhythmites. A Rhythmite is a rhythmic deposition of two couplets. In this case, it's generally sand and silt. There's exceptions to that, but in generally sand and silt. I'll show you a picture of that. But anyway, this is near Pasco, Washington, looking southwest through Wallula Gap. Now, when the water got down to south central Washington, it couldn't get through this gap, which was more narrow at one time. And so the lake built up 600 feet deep here at this location. And it sent pulses of water up the Snake River, up the Walla Walla River, and the Yakima River, and a few other rivers. And those pulses form the Rhythmites, which I'm going to show you. Here they are at, it's called Burlingame Canyon. You see the man for scale right up there. That's Dennis Buckavoy from Hood River, Oregon, I might add. And you can see the Rhythmites. Very Rhythmite. They look exactly like sedimentary rocks, except they're very soft. In fact, I've been down this twice. You have to, it takes a lot to get permission to go down here because it's dangerous. This is all soft material. So I've been down to the bottom of this and I've been to the top. And you might notice in the background another ridge, like the Saddle Mountains. This is Horse Heaven Hills. And these Rhythmites do not continue out in here. I'm going to talk a little more about that as we go and what the significance of that. These Rhythmites are in the middle of the valley. The Wallula Valley is generally east-west, about 25 miles long. And these rhythmites are in the middle of the valley. In fact, it's so flat on these rhythmites that they put an irrigation canal on the top. In fact, this is how this canyon formed. It formed in 6 days in, I think, the 1920s, when a huge wind was filling up the irrigation canal. They're afraid it was going to flood into the fields. This is all farmland in this area. So they bled off the water from the irrigation ditch into this outflow area. But the sediment was so soft that it carved this canyon about 100 to 125 feet deep in 6 days. It's about 1,000 feet long. And it shows the rhythmites perfectly. And anyway, near the top up here, there's an ash layer. You can't see it in this photograph, but here it is. It's an ash layer from Mount St. Helens. It's, yeah, right in here somewhere. You see it, this is in the Yakima River Valley. This is the Yakima River to the left, and here's one location of the rhythmites. You can see the white ash near the top, right in here and right over here. So he said each one of those rhythmites has to be a separate Lake Missoula flood because it's just improbable that they both happen at the same time. So he claimed that after one Lake Missoula flood, then you had the ash from Mount St. Helens fall over, and then it was covered up by another rhythmite. But of course, you know, when these floods move up the Walla and the Yakima River Valley, they're moving pretty fast. So it's a specious argument, as I'll get into. Anyway, those are some of the pictures. Anyway, I don't know. Anyway, the volume of water in Glacial Lake Missoula was about 4 to 5 times the volume of Lake Erie. Just imagine that breaking through an ice dam and spreading out. It gives you an idea what the Genesis flood can produce. The Genesis flood can easily produce a huge amount of sediment, which a lot of critics think it can't. But the Lake Missoula flood carved up 50 cubic miles of hard basalt and soft silt, and from one flood. But anyway, to continue the theme of how many floods, the rhythmites, there's about 40 rhythmites in the Burlingame Canyon. So Richard Waite said, well, that's 40 floods. Okay. Then a man named Atwater was his last name, can't think of his first name, did some research north of the former glacial Lake Columbia, which is north of the current Lake Roosevelt, backed up by the Grand Coulee Dam. And he found these rhythmites, the Sandpoil Valley. And these were a combination of what looked like flood layers separated by varves, rhythmites, right in here. Here's a close-up. These are what's called varves, which are believed to be deposition, yearly deposition, with the coarser layer being from the summer and the finer layers being from the winter. So each one of those is supposed to be a year. And based on this, and he did a core, and he found 90 of these things. And so they claimed there was about 90 glacial Lake Missoula, all at the peak of the last ice age, I might add. Not to speak of the other 50 ice ages they claim for North America, various intensities. Maybe only a dozen were intense enough to glaciate northern Idaho. But anyway, we won't get into that issue. That's a separate red herring, which I thought about. Anyway, Well, there's a number of problems with this idea of multiple floods. Here are 6 of them, and I'll talk about a 7th one after this that I could add, that I will add. Anyway, Glacial Lake Missoula produced some sediments on the bottom of the valleys. And a man did a PhD thesis and drilled the sediments north of Missoula. And he discovered that, well, it looks like the sequence of one filling of Glacial Lake Missoula with one monstrous flood. Because if you had 90 separate floods, you'd have to fill Glacial Lake Missoula 90 times. And you don't see this kind of a pattern in those sediments. It looks like it's just one filling. I'll get into this in more detail. And here's the PhD thesis right here, which I will quote. It's from the University of Colorado, Daniel Levish. He says, because there are no identifiable breaks in the stratigraphic sections down to the bedrock, he probed down through the sediments to the bedrock. The entire section represents the last high stand of Glacial Lake Missoula, and therefore is late Wisconsin in age. Of course, that's where they put it, their time scale. This stratigraphic evidence from the Mission Valley does not confirm 40 to 90 latest Pleistocene Glacial Lake Missoula catastrophic outbursts promoted by Waite and Atberg. So anyway, he doesn't see the separate fillings, which should easily be seen in the lake bottom sediments. Now, the Sandpoil Valley, now, if you had 40 to 90 floods, those floods are going over basalt. And so as they backwash up the Sandpoil Valley, forming that pattern of flood sediments followed by rhythmites. The rhythmites, or the varves, are supposed to represent maybe 40 or 50 years between floods. That's what, and so you have maybe 3,000 years in this sequence, something like that. And so as the flood broke in northern Idaho and spread through eastern Washington, it should send basalt rocks up the Sandpoil Valley, but there's no basalt rocks up there. Here's the Sandpoil Valley right here. It's near Grand Coulee, just on the other side of Grand Coulee. So there should easily be basalt in there, but there is no basalt, indicating that those rhythmites came down from the north, not from the south, from a Lake Missoula flood, probably from the melting of the Cordilleran ice sheet that covered northern Washington, and actually blocked the Columbia River in this area, forming Glacial Lake Columbia. So these are probably represent yearly melting, and they're not varves, they're rhythmites formed catastrophically quickly, is what I believe they are. Also, when you look at the rhythmites, there's no erosion within them. Notice how even they are. Kind of like the Grand Canyon, where you don't see erosion between all the layers, even though in Grand Canyon it's claimed that this horizontal strata was deposited over 250 million years. Well, erosion's so fast you can erode all of North America to sea level in 10 to 50 million years. If erosion's that fast in a million-year time scale, there should be huge canyons and valleys seen on the walls of Grand Canyon, but there are none, indicating a rapid deposition of the sediments, some of which can be traced over half of North America, I might add, like the Tibet sandstone on the bottom on top of the igneous and metamorphic rocks. So that's the same thing you see in the rhythmites and the Wallula River Valley at Wallula Gap, like here. And this is a typical, here's the sand layer down here at the bottom, followed by a thick silt layer. So pretty even, each one. And now, one of the significances is that if these are separate floods, when the flood is rushing down eastern Washington, moving 60 miles an hour and backwashing up these valleys as the lake built up to 600 feet high at the Pasco area, it's going to be rushing up these valleys. And as it rushes up, it's going to erode a huge amount of material that you don't see in these rhythmites, indicating that the rhythmites are from one monstrous Lake Missoula flood. Also, these rhythmites thin upwards. They're about maybe a meter thick at the bottom, and they thin to maybe 10 centimeters at the top, which you'd expect from pulses from this 600-foot deep lake pulsing up. They pulse up rapidly and with the most sediment at the beginning. And as it slows down, as the lake reaches 600 feet tall, the amount of material being pulsed up is less. And so the rhythmites deposition becomes less. And then finally, the lake drains. And as the lake drains, probably drained in about 2 days, all this water comes rushing back towards that lake from those valleys and goes through Wallula Gap into the Hermiston area, down the Columbia River, into the Portland, Vancouver area. That's what should happen on each one of these flood. Eroding out, should erode everything. These should have no rhythmites except the last set. The fact that they thin upward is what you expect from one giant flood that tailed off. Also, there's something in these rhythmites called clastic dikes. This is vertical or cracks. The dikes are not necessarily vertical, but sometimes they go at an angle. Sometimes they're pretty wide of material. They're mostly sand and silt, like the material of the rhythmites that cut up. And these dikes go from the bottom to the top, representing a dewatering pattern for when the lake that ended up in these areas, when you form that lake 600 feet deep and the pulses stopped and then it drained in 2 days, it saturated water in there and it's going to come up from the bottom to the top, forming these classic dikes, making a lot of sense for one Lake Missoula flood. Now, if these classic dikes were from individual floods and the rhythmites are about this thick, you should have classic dikes that are only short and then they truncate right before the next one. And then you should have another set for the next rhythmite. It's not like that at all. It's from bottom to top, as I will show you. Here's one right in here. Here's another one over in here. I'm told from the farmers that they form a polygonal pattern on the surface of the farmland at the top. Classic dikes. If each one of these is one flood, that you'd have numerous sets of classic dikes that are only as thick as each rhythmite. They'd stop there. And look at how they're thicker rhythmites down lower and they thin towards the top. These are easy to see features, I might add, which makes you wonder why the multiple flood Lake Missoula flood theory is so popular now. It's the consensus. Anyway, the last one is rhythmites are in front of Wallula Gap. Remember, Wallula Gap is where the water is trying to rush through. And the fact that there's rhythmites right in front of it, where you expect really fast water rushing out, should erode the whole thing. But there's about 20 rhythmites in places in front of the gap, probably spared, probably eroded only a little bit, spared because of maybe an eddy from the water moving out. Here's a picture of them in front of Wallula Gap. Now, they're not very neat because they're just not. And you see some of the classic dikes through this material. But if you can put a slice down here, they'd look like Burlingame Canyon because of erosion and rain and all that. They're partly eroded. You can't see them very well, but they're there. Now, because of the controversy over the number of floods, John Shaw and 7 geologists from the University of Alberta in Edmonton came down with no position of whether there was one flood or multiple floods, and they decided to look at it afresh. So they went all over the area. And they wrote this article that was published in the journal Geology called the Channeled Scablands. That's what they call Eastern Washington, because when it carved up the silt down to the basalt is really rough, basin and butte topography, which you can't farm on. Maybe some cattle can live on it, but it's really rugged. And so it's called the Channeled Scablands. When they say back to Brett's believed in one flood. Anyway, here's what they say. Recent sedimentary investigations of some sites in the Missoula Basin and in the Channeled Scablands support a single large Lake Wisconsin flood as opposed to multiple floods proposed for this time. And I have a further one to add, a seventh piece of evidence. In an earlier paper, I fleshed this out a little better, but this is, you're looking south, and this ridge in the background is called the Horse Heaven Hills, one of those lava ridges, about 7 lava ridges in that south central Washington area caused by north-south compression of the basalt, which I might add is about 4 kilometers thick in that area. But anyway, you can see it's about 100, this canyon is about 1,000 feet long. And as you get out here towards the edge, it's totally eroded south of this. You're out in the middle of the valley here. And this ridge out here is about 3 miles out. And they're totally eroded between this area and that ridge. The same feature occurs to the north of this. This is a ridge right in the middle of a valley. It's about 8 miles wide. The ridge is right in the middle. And the Rhythmites are not found along the edges. They're totally eroded. In fact, you can see that erosion has truncated them. Now, if each one of these is one flood, and they're building up on these Rhythmites in this area right in the middle, it would form a pattern that covered it, and it would, along the edges, it would drape. You see drapes, but it's not a draping pattern. They're formed over this whole area, valley, and they got totally eroded, or almost totally eroded, to the north and south of this east-west ridge. Then this is what you'd expect from one filling sending pulses up. These are each one's a pulse, as Brett's thought, and also Victor Baker thought originally. He's done a lot of study of the Lake Missoula flood and Channeled Scablands. Anyway, after the pulses stop and the water's moving out at high speeds, it's mostly eroding. So you not only form these over the whole area, but you eroded about 95% of it, mainly along the north and south edges of the valley. So that's a signature of one monstrous flood. Anyway, let's get into what this all teaches us. The third point out of 4. Secular scientists are biased against catastrophic process. This isn't much news, but their bias runs deep, very deep. And it was represented by the Lake Missoula Flood Controversy. When Brett's first discovered it, they criticized him and challenged him tremendously. Here's a little quote. The establishment, that's the establishment geologist, as represented by the United States Geological Survey, closed ranks in opposition. Instead of testing Brett's theory on its own merit, they rejected it on general principles. And why did they do that? Well, a 2016 article in Nature kind of gives you the idea why. When geologist J. Hart, by the way, the letter J is his name. There's not a J dot there, and it's not J-A-Y, it's just J. Anyway, J. Harlan Brett's proposed in the 1920s that the Channeled Scablands were created by a catastrophic flood. His ideas were attacked relentlessly by geologists. Sounds familiar, doesn't it? Who subscribed to the mainstream view that erosion is slow and steady, and who wanted to distance themselves from their profession from the notion of a biblical deluge. In other words, they are so biased against the flood that they rejected the Lake Missoula flood for 40 whole years until the 1960s, when Brett's being, I think, in his 80s, and a team went out there and had aerial photos. And guess what? There are hundreds of pieces of evidence for the Lake Missoula flood. Of course, most of Brett's critics never went out to check it in the field, but still, there were some that did check it, and that didn't help. The renowned glacial geologist Richard Foster Flint went out there and investigated for quite a while and wrote a paper that essentially said it was all can be accounted for by slow processes of erosion over hundreds of thousands of years, if not millions. In other words, he had his uniformitarian glasses out there and he totally failed to see all that powerful evidence, which is really obvious, hundreds of pieces. And because of that, I do not expect a secular geologist to actually see much evidence, if any, of the powerful evidence of the Lake Missoula, of the Genesis flood, especially the runoff part. With John Reed and Peter Clever, again, I have made an estimate based on the amount of ocean sediments. I think that was one of my talks, that an average of 1,900 meters of erosion occurred on the continents during the recessional stage of the flood as the flood waters were running off. And it left behind features that they can't explain in the field of geomorphology. In fact, that's the subject of my ebook on my website. Color pictures, 80 some chapters, I think about 800 pages. I never counted it. But I go through all this geomorphology systematically, and I published articles and papers on it widely. They can't seem to see any of that evidence, but it's really easy to see, really easy. So I don't expect too many of them to really see it because there's a ton of evidence for the Genesis flood. And why? Because their minds are so locked in concrete with uniformitarianism that I think it's kind of a blindness. I came across this quote from a book, The Promise of Sleep. I was a shift worker for 30 years and had sleep problems for 50 years, but thank the Lord, not for the last 7 years. And I came across this quote. William Dement was as a researcher from Stanford University on his sleep research. He was one of the discoverers of REM sleep. He says, even when they are looking, people usually see only what they expect to find, and they do not see that they assume for whatever reason could not exist. So they don't expect it, they don't see it. It's an amazing thing. And I tell you, us creation scientists could get in the same rut. So we need to make sure that we look at all sides of an issue, look at the data carefully, try not to jump to conclusions too quickly. I try to do this. And that's why it takes me a long time to do research. A lot of these research projects take me years sometimes because I'm still looking at the data. I believe in looking at the data first. Okay, number 4, as I kind of hinted at, we can use the Lake Missoula flood as an analog for Noah's flood. Okay, how is that? Well, it's a runoff. Once the Lake Missoula flood broke through the ice dam, it just ran off. And what did it leave behind are similar to features left all over the surface of the earth, of the continents, from the Noah's flood, indicating that a giant flood eroded the surface of the continents, an average of 1,900 meters, leaving these telltale features. I'm going to talk about 3 mainly. There's a few others that they weren't so solid, so I don't get into them. Number 1, erosional remnants. 2, water and wind gaps, and rapid deposition of the continental shelf and subsequent submarine canyons. I'll flesh this out. We're getting near the end of this presentation, by the way, so if you have questions, start thinking about them. Anyway, floods leave erosional remnants. This is a flash flood in a field in South Africa. And it eroded the field, but it left erosional remnants of various sizes behind. But as time would go on, these erosional remnants should erode and flatten out, and you shouldn't see them in a short time. So it indicates not only a flood leaves erosional remnants, but it was a quick flood, and not that long ago. So here's some of the erosional remnants from the Lake Missoula flood. I pointed out Umatilla Rock down below Grand Coulee as one. But here is, I showed this picture earlier. This is the upper Grand Coulee. And here is Steamboat Rock seen in the background. And there it is. It's about 1 square mile at the top. It's 900 feet tall. And you can actually hike up the top of it right through this area right in here. And you get a great view like this. You can see the trail below. And this is called Banks Lake, a lake that formed the upper Grand Coulee. And it's one interesting thing about this, there's glacial erratics on top of it, like this one right here. So what you're seeing here is the edge of the Cordilleran ice sheet in this area, right at this area. And that's probably what channeled the floodwaters of Lake Missoula flood along the edges of the ice to carve up a gorge right along the edge of the ice in the upper Grand Coulee. Then 25 miles south, it hit the Coulee monocline, which is a real weak area, and took advantage of the cracks and the weakness there to form the lower Grand Coulee. Total of 50 miles. Really impressive stuff. So, are there erosional remnants on the continents? There are thousands of them, and a lot of them are vertical and tall, implying that the flood was not only quick, but it was recent, because with further erosion should all erode down quickly. My favorite erosional remnants is Devil's Tower in northeast Wyoming. It's the throat of a volcano, very likely. It's about 1,000 feet wide, and it's about 1,200 feet above the rivers to the north and south, the river valley you see here, and about 900 feet above the plains, this level of the plains. So if it's the throat of a volcano, when the volcano was going off, it was sending up lava through this conduit 1,000 feet wide, up, and a volcano that would be up in the air quite a bit. Now, these conduits don't just sit and form an air. It implies that you had sedimentary rocks, at least to the top. Secular scientists think it was 2 to 3 times the top. So the sedimentary rocks in the plains were way up in here. They're probably correct. And they all got eroded down, leaving Devil's Tower hardly touched by erosion. The width hasn't changed hardly at all. But currently it is eroding fast because it's like a basalt columns. It's not quite a basalt, but it's cracked. And water gets in those cracks, freezes, and pushes out the rocks and forming this talus. There's not a lot of talus below it, indicating it's a pretty young feature. Similar to a lot of other places in the western United States, a lack of talus for the supposed millions of years old. This was once thought to be 40 million years of erosion, where it started at the top down to here, but they realized probably that didn't make sense because vertical slopes should erode lots faster than horizontal surfaces. That's the key on there. Vertical slopes, like you see here, should erode much faster. So this should be a pile of talus in maybe 10,000, 50,000 years, very short time. Yet the secular scientists once said it was 40 million years that the sediments had eroded down to this level here, this rougher area at the top. but now they're saying it's only at 2 million years for this sequence. So regardless, even 2 million years is way too long for this to remain like that. This is indicating a rapid flood that, like the drain off the Noah's flood, rapidly eroding the material all around, and for some reason leaving this erosional remnant. Maybe because it was harder rock, maybe because there was an eddy in there. There's several, or the current's slow. There's reasons for this, but there are thousands of erosional remnants, some similar to this around the world. It's a global thing, indicating a global flood, not a local flood. Another erosional remnant, out of the thousands, is Ship Rock in northwest New Mexico. This is another throat of a volcano, but this one's 1,700 feet above the flat plain around this. And this is a conduit of a volcano, and the sediments were really high in here, and then eroded down to this level, leaving this as an erosional remnant. If it was done over millions, even a couple 100,000 years, this would be a pile of talus, but there isn't much talus here. Another famous area of erosional remnants is this, and this kind of combines the amount of sediment deposited on the continents at the peak of the flood, which is approximately day 150, and then the erosion of about 1,900 meters average. So you have massive deposition of sediment. John Reed, I, and Peter Kleberg have estimated that the amount of sediments at the peak of the flood average on the whole continent is about 3,500 meters. And the top 1,900 meters of that was eroded, leaving maybe about 1,500 meters left on the average, at least on North America. We're doing calculations on figuring that out right now. Anyway, this is the peak of the flood, day 150. And then during runoff, it starts eroding down, down, down further, and keeps going, leaving erosional remnants, indicating a rapid flood runoff not that long ago. Monument Valley, of course. And by the way, this sediment up, it's sandstone and shale below. That sandstone is not very hard. You can go up to it and rub it off with your fingers. It's a real poorly lithified or hardened sandstone. So they're not going to last more than 10,000 to 50,000 years. But I'm sure the secular scientists say that these have been here for millions of years. Anyway, that's erosional remnants. Now let's talk about water and wind gaps. The Lake Missoula flood formed a number of water and wind gaps. The most famous, the best examples are in south central Washington, where the floodwaters were moving south and overtopped a ridge between Washtutina Coulee and the Snake River. Here's the Snake River coming from the Blue Mountains down like this. And here's Washtutina Coulee like this. Now, the Palouse River used to run into Washtutina Coulee and enter the Columbia River. But then the flood coming down from the north eroded the top of this 500-foot ridge between Washtutina Coulee and the Snake River and carved a water gap right here that starts about 8 miles wide and narrows to a very narrow canyon. And then it carved another canyon called Devil's Canyon. Now, the Palouse River, after the Lake Missoula flood, instead of continuing down Washtutina Coulee, it takes a left-hand turn right here and passes through the water gap into the Snake River. Now, this, if there was water up in here, it can't flow through here because there's a high boundary here, so it's a wind gap. A water gap is defined as a gorge through a ridge or mountain or plateau where water starts on one side and passes through to the other side. A wind gap is not carved deep enough, and it's where wind is only passing through it today. So here's some pictures of it right here. This is the narrow canyon. This is the Palouse River down here near Palouse Falls. It even meanders, as you see. And you can see some of the basalt flows of the Columbia River basalt in here. That's probably a couple kilometers thick. And here is the entrance to Devil's Coulee. And here's this little high area. So if there's water in Washtutina Coulee, it can't go that way because of this higher area. And this canyon is about 500 feet deep in the basalt. And you can drive down through it. And you can look back up at it right in there. So that's a wind gap formed by the Lake Missoula flood. There are thousands of water and wind gaps across the earth. Thousands. Secular scientists had four or five theories on their origins, but they can't prove any one of them. A lot of problems against these ideas. You can check my website where I go into the secular ideas on the formation of water and wind gaps. My favorite water gap is near where I live. This is looking west toward Yellowstone Park. This you can't see in the background. To the east of Yellowstone Park, here are the Rattlesnake Mountains, they call them. It's an uplift, 2,500 feet tall, and I'm looking west. The Shoshone River starts in southeast Yellowstone Park and moves west down a valley. Moves east down a valley and continues through this water gap that's 2,500 feet deep, carved in hard granite in the middle with sedimentary rocks banked up on both sides. And this ridge is a plunging ridge. It used to go like this and down like this, and it disappears 2 miles to the south. So the Shoshone River could have easily gone around this if it was a slow erosion over millions of years. Should have gone around it because it's a very low area on the other side of this. I'll show you. Here's the other side. This is the water gap right here. Shoshone River continued moving straight east without being deflected. And it could have easily been deflected if there was no gap there down this way, because it's very low, as you see, and wide. In fact, it's so low when they put the dam in here. They put the dam in the water gap, by the way. They had to make another dam here to the south so that the water of the Buffalo Bill Reservoir wouldn't spill out into the Bighorn Basin. So how does that happen by slow processes over millions of years? They really have great difficulty with these hypotheses. And I might add that since they can't think of this forming during the flood, they're left with slow processes over millions of years. So that's what they go with. And so they're not left with a theoretical vacuum. They always seem to have some kind of hypothesis, secondary hypothesis. And I would say practically all of them are ad hoc in this case. In other words, without real evidence of how the Shoshone River ends up going through this water gap. There's a lot of other water gaps. Like I said, there's thousands of them across the earth. Here's one. This is the Green River. Starts in southwest Wyoming and flows south, hits the Uinta Mountains, actually starts going through the Uinta Mountains and then comes back out and then continues east. And it could have gone around the eastern edge of the Uinta Mountains in a very low area. But instead, 3 miles from the eastern edge of the Uinta Mountains, it ends up passing through a narrow slot canyon, a half a mile high, through hard quartzite in the core of the Uinta Mountains. Now, how does river do this? Well, the upshot is they don't. But we can easily explain it. It's really easy in that you remember the waters are running off and the land's coming up. The mountains rose, the valley sank down some 104.8 to drain the floodwaters. And a lot of times, widened currents were going perpendicular to a mountain barrier, a ridge, and they would be, and no ridge is perfectly flat, so there's low spots and high spots. And the water would end up carving through the lower spots like this, especially when the ridge is emerged above the floodwaters, and going around it, this like this. And but when you do that, when the ridge emerges, you've got to send the same amount of water upstream through these more narrow areas downstream. So the water has to accelerate in order to do this. It's just like passing the same amount of water from a wide pipe through a narrow pipe. The flow has to speed up. And this would be the case. It would speed up and carve these gaps quickly because in general, erosion's to the fourth power of the velocity. So if you double the velocity, the erosion goes up approximately 16 times. So these would be carved rapidly during flood runoff. And then because of switching currents or whatever, this is just a schematic, remember, gives up. And all the flow ends up going through this. And so at the end, this is carved all the way down, and where the rivers can now flow from one side of the mountains to the other. This one is left high and dry, and it's a wind gap where only wind is going through it. A lot of times wind gaps are passes through mountains because they're usually low areas through the mountains. Sometimes they go right through the water gap, like they do at the Shoshone water gap that I showed you. So the Lake Missoula flood formed erosional remnants and water and wind gaps, just like we see on the surface of the earth of the continents by the thousands. Also, there's an analog for the rapid deposition of the continental shelf and subsequent submarine canyons. When you eroded 1,900 meters average from the continents, it had to go somewhere. It's going to be moving likely at high speeds due to the potential energy of the continents coming up and the ocean basin sinking differentially. When I say differentially, I mean it could be the ocean basins only are sinking or the continents only are rising. But regardless, it's with regard to one or the other you have in this. And you find tremendous change in altitude of the water on the continents versus the ocean. So it's moving at high speeds. But it's going to slow down where it hits deep water. And it's going to drop its load along the edges of the continents, forming the thick continental shelf off the coast. The average thickness of the continental shelf is 3,000 meters. Some of these are so thick that they're up to 18 to 20 kilometers thick in a number of areas. For instance, off the east coast of the United States, the Bay of Bengal, Gulf of Mexico, and off the Arctic coast of Siberia and Alaska, you have very thick margin sediments. But after you deposited this material as a sheet all along the continents, the water is forced to channelize when more mountains and plateaus appear, and the water is channelizing. And as it's channelizing, it accelerates and erodes valleys that are on the current continent, and it brings that debris out on the continental shelf that sloughs down the continental slope, forming submarine canyons. So we have a little analog. It's not the best analog. With this diagram, I showed you what's called the Portland Delta. So as the waters were coming from the east, 1,000 feet deep through the Columbia Gorge, forming this huge gravel bar, 200 square miles, 300 feet deep of sometimes huge boulders. After deposition of all that, even in this blue area, then they channelized more as the waters were coming down. They channelized more through this and carved this. So this is a rough analog of the deposition of the continental shelf, this delta, followed by the rapid erosion for the submarine canyons. And here's a submarine canyon. There are several hundred of these that incise the continental shell sediments, which are very shallow, I might add. Here's the one at Monterey Bay, Monterey Canyon. It's a mile deep. It's the size of Grand Canyon. And here's Carmel Canyon that goes into it. And this canyon goes almost up to the shoreline. That's Monterey Canyon. Now, the picture I took didn't do very good. I'm not very good at filming these things. The flash bounced off of it. But I don't have access to this picture anymore. So you have an analog for formation of the continental shelf sediments, which are very thick. And a lot of them, they shallow out for sometimes a couple 100 kilometers out, and then they drop off, forming the slope. And then they're cut through that. So the shelf mostly formed first, followed by the canyons afterwards. So in summary, there are hundreds of pieces of evidence for the Lake Missoula flood. There's only one Lake Missoula flood. Committed secular scientists will have great difficulty seeing evidence for Noah's flood. We learn about catastrophic processes, especially flood runoff, but even erosion, because of the 50 cubic miles of basalt and soft silt that was eroded, catastrophic erosion. And we can understand enigmatic features on the Earth's surface uniquely caused by the flood, mainly the flood runoff. And if you want to know more about this, Kyle Justice in Awesome Science Media filmed me for about 100 minutes out in the field showing you these things. This is just not a talking head. But anyway, this is a DVD resource you can get from a lot of the creationist organizations. And of course, this is my main book on the topic, the Missoula Flood Controversy and the Genesis Flood. And if you want to know more about the Ice Age, you can check into this book, Frozen in Time, The Woolly Mammoth, the Ice Age. And actually, it's been retitled to the Biblical Key to Their Secrets. And Awesome Science Media shows another approximately 100 minutes of me out in the field of the Northwest states, United States, showing you glacial features that there was an ice age. Anyway, that's all for the advertisements. Thought I'd throw in a few resources for people that want to dig a little deeper. I don't normally do this in this presentation, but there's 4 of them for you. Anyway, I'm ready to entertain questions, especially those 2 main questions you sent me today.
Mike, you can never have too many resources, brother. Right. So I appreciate that. The Missoula Flood DVD is excellent.
Thank you.
Greatly filmed. The production value on it is awesome. In terms of this presentation, I appreciate how you demonstrated thoroughly. We love how comprehensive your presentations are, Mike, but you demonstrated how it's one flood, one Missoula flood, and how its associated geologic features provide us excellent testimony, or it's a small scale example of the Genesis flood, which, contrary to local flood theorists and proponents, was a worldwide event.
Yes.
Excellent presentation, Mike. Before we get into the 2 questions I sent you specifically, and then the next about 100 questions coming in from the audience.
No.
Matt, any thoughts from you, brother?
No, that was great. Love the technical aspect, and I like the Devil's Tower. That's unique. My friend goes down there because he is a stonemason and cutter, and he gets the basalt that falls from it all the time, and brings it back and cuts it and makes designs and things like that. So it's pretty neat to. There's people crazy enough to actually climb that. Did you know that? It's
I do know that. Yes, I do know that.
Very dangerous. They do not recommend it.
Yeah, and I might add that people who live near there can hear the erosion of those blocks every winter crashing down. So it's actively eroding.
Wow. Yeah. Online, it was popular for a while. People thought it was a remnants of a giant tree.
Yeah.
Well, Mike, as you obviously know, since you're the one that gave the presentations, we did a series here with you on the pre-flood flood boundary and the post-flood boundary.
Yeah.
And both those programs received a lot of excellent feedback. I've gone through those presentations thoroughly many times, and I know many of in our audience have as well. And so I'll start with a couple of the questions that I sent you. Now, I know this topic of flood boundaries is controversial in the creation world, but it's an important topic.
Yes.
And so the first question, and I'll lay out the context for it. So basically, those that would hold to a lower flood boundary rather than a higher flood boundary, like the late Cenozoic boundary model, they would argue that there is a significant decline. And they argue this in support of the lower flood boundary model. They'll argue that there's a significant decline basically in the amount of catastrophism taking place as you move up in the geologic column. And so the higher you get up into the Cenozoic, it seems less and less of the material is being formed from large scale catastrophe and more towards small scale ones. And the intensity of events are gradually being dialed down as you move higher and higher up into the Cenozoic, especially in terms of North America. What are your overall thoughts on these points, Mike?
Well, right off the top of my head, I would say that's what we expect at the end of the flood also, that it's going to be dialed down. So the deposition is going to be over smaller areas, so you expect smaller formations. But I might add that a lot of these Cenozoic formations are not that small. The Fort Union Formation, where I live, in Montana east of the Divide, adjacent Wyoming, South and North Dakota, is probably hundreds of square kilometers in area. And it's an erosional remnant. There was a lot of material on top of this. There's a paper coming out in the CRSQ where we can show 1,000 to maybe 2,000 meters of erosion in the Great Falls, Montana area. And the Fort Union Formation is about the lowest formation around. So I actually have a lot to say on that, but I have a few slides I want to show on this catastrophism that's supposed to be so violent at the start and then tailing off. It's actually violent at the start. This is from John Reed, new information. We haven't published it yet. The continental crust of the Earth is full of cracks, huge cracks called rifts. Here's the most famous is the mid-continental rift. It's about, we should have a scale on that. It's about 2,000 kilometers long. It forms a horseshoe shape like this. And it's about 50 miles wide. And here's some of the depths. You can't see these very well, but this blue area is 80,000 feet carved on top of the upper crust, deep. Monstrous crack. Then you have these basins like the Williston Basin, very circular, and the Michigan Basin, which I think are impact craters, which shows up pretty well on another slide that John Reed did. And there's other basins. So the continental crust, which I believe represents early flood, the rifts and the meteorite impacts. Now, some secular scientists have leaned towards it. These are meteorite impacts, but guess what? They get shot down. But it has many of the signatures of an impact crater that's filled in rapidly with sediments. So that's catastrophism at the beginning. So I totally agree that we had catastrophism at the beginning, but we had to have a lull in the middle. Why? Because when you look at the Grand Canyon, the sediments of the Paleozoic, you're seeing the Paleozoic here, 4,000 feet, they're evenly deposited with little faulting showing up. And then to the north, you have the Grand Staircase. See, this represents an erosion of maybe 8 to 12,000 feet, depending on how thin the layers were above, of strata. All over the Grand Canyon area was taken off as a sheet, leaving the Grand Staircase to the north. And these sedimentary rocks are pretty evenly bedded too. And this is mostly Mesozoic. So the Paleozoic and Mesozoic, including the Grand Canyon, the Grand Staircase, you have about 14,000 feet of strata deposited with little or no deformation, indicating, and I don't think this is a rare situation, indicating slow deposition. I mean, little vertical tectonics. So you had to have a lull to form this sediment pattern. And then in the early Cenozoic, you have an increase in catastrophism where practically all the mountains of the earth rose during the Cenozoic, including the mid and late Cenozoic, I might add. Sometimes 40,000 feet in the Western Rocky Mountains, or the Rocky Mountains where I live here, starting in the early Cenozoic. So that's powerful catastrophism. I think that's what drained the floodwaters, was that catastrophism. And then you eroded 1,900 meters of the top of these sediments. Here's a block diagram. It's a schematic illustrating the current continental sedimentary rocks. We don't know the depth. We've been calculating, John Reed's been calculating them on North America. We're getting numbers about 1,500 meters average left down to the bedrock, mostly the upper crust, granite upper crust. And then 1,900 meters of the top was eroded off. So at the peak of the flood, you had 3,500 meters of sediment. And that got eroded off. Now that's pretty powerful catastrophism. So the upshot of what you see in geology is tremendous catastrophism at the beginning of the flood. And this formed the Great Unconformity at the same time, I might add. It takes time to form the Great Unconformity. Some people think that that's the precise boundary at the beginning of the flood, but no, that takes time to erode down maybe several miles to that generally flat erosion surface that you see in Grand Canyon, you see in my area, you see in the Continental, the shield of North America. So it takes time for that. So I definitely don't think the beginning of the flood, pre-flood boundaries at the Cambrian, Precambrian, at the Great Unconformity. It takes time to form the Great Unconformity. So after things settle down, you start depositing all those sediments without much vertical tectonics and catastrophism until towards the end. When the mountains rose, the valley sank down. And that all happened in the Cenozoic. So it was a two-part catastrophism, and geology shows that very well. In fact, John Reed had a plot he published 15 years ago on the energy of the flood, which is proportional to catastrophism. He had high energy at the beginning, lower energy towards the middle, and then higher energy again towards the end. So that's what I believe answers the second question, which and some of that erosion, let's see, was this going to be into the second question? I'm thinking. Yeah.
Yes.
No, this is an example of some of the erosion that I did a trigonometry calculation over the San Rafael Swell, the northwest Colorado Plateau, where I got an average of 4,200 to 5,000 meters of erosion right near the top of the San Rafael Swell, based on trigonometry from this pass right here to about Helper or Price, Utah. 25 kilometers base. These tilt down to the north about 8 degrees. So by trigonometry, that's what I arrive at. And even to the north, there's about 2,000 feet of erosion in here. And I might add, you notice the top formation is the Green River Formation. This is considered a result of deposition of a post-flood lake by some creation scientists, but I find obvious evidence that that is not the case. It has enough oil to supply the energy needs of the United States for 100 years. It has tropical fossils like palms and crocodiles as fossils in it. And this straddles the Continental Divide in Wyoming. So it's an inland area, continental climate, high altitude. So we wouldn't expect post-flood palms and crocodiles. And besides, it's very thick. And if this is all post-flood, you have to think of this area forming the lake, depositing several thousand feet of the Green River Formation, bowing up the San Rafael Swell, eroding this whole area, part of the Colorado Plateau erosion, and eroding that much. And the material is not found nearby, but is totally swept off the continent. To me, and this might step on the toes of some creation scientists, to me, there's obvious big picture evidence that the Green River Formation is from the flood. Now, exactly how it formed, that's a whole different research project. So I can't tell you more because it's a difficult feature to figure out. But the big picture indicates it's from the post-flood. Let's see. Now, how was I going to relate? Oh, that's just part of that catastrophism late in the flood. This is just an example of the erosion late in the flood. Anyway, the second question, you want to get into that?
Yes, and before I do, firstly, great answer. You said some of the mountains arose 40,000 feet during the Cenozoic?
Yeah.
Wow.
For instance, I can show this in the Uinta Mountains. I did a 2-part article that was published maybe 15 years ago in the Creation Research Society Quarterly. And the Wasatch Formation was deposited first. That's early Cenozoic. Over the top of these other Mesozoic, Paleozoic. There's a general sequence of the geological column in the Western Mountains, I might add, general. And the uplift did not start until the early Cenozoic Wasatch was formed, and then it rose 40,000 feet in the Uinta Mountains and sank. It rose up to 14,000 feet above sea level and then sank something like 25,000 feet below sea level in the Uinta Basin to the south. So that represents a change of 40,000 feet for the Uinta Mountains. And you can show this in other mountain ranges of the world too. All through Wyoming, you can show up to 45,000 feet of differential vertical tectonics where the mountains rose, the valley sank down, and it occurred in the Cenozoic. I have, check my website, michael.ords, OARDS.net, I think. And you can see several chapters on all this stuff.
In order to buckle the rock strata to rapidly lift those mountains, you'd require catastrophic processes, the type associated with the flood, correct?
Oh, yeah. Yeah. To me, to think of those being post-flood, that's one of my 35 evidences of this tremendous uplift. And this is global, like this amount of uplift is one of my signatures of a flood signature, because you wouldn't expect that after the flood at all.
Right.
But during the flood, you would to drain the flood waters, according to Psalm 104:8. So yeah, and it practically all occurred in the Cenozoic. In fact, there are 2 geomorphologists, Cliff Ollier and Colin Payne, that wrote a book on the origin of mountains, published in 2000, and they republished information on the high mountains and when they when they uplifted, with table going through most of the mountain ranges of the world. That's published in a Russian journal. I think it's going to be a perspective article that's going to come out in the journal Creation down the road. It still hasn't been reviewed yet, or maybe it has been. I can't remember. But anyway, they list them, and they're all in the Cenozoic. A lot of them in the late Cenozoic. So
Wow.
indicating that you had powerful catastrophism during the Cenozoic.
Right. Therefore, if someone were to hold to a KPG boundary, a lower flood boundary, would they have to argue that your mountains started to uplift at the end of the flood, but rose higher and higher in the pre-flood world?
Not the pre-flood, you mean the post-flood?
Or the post-flood world?
Yeah, I guess so. But the main uplift and sinking of the adjacent valleys, it's very common to see adjacent to high mountains valleys that go way down, like
Right.
south of the Himalayas. You have the Ganges valleys, which represents, I'm estimating maybe 7,000 meters of sediment collected in there. So the Himalayas and the Tibetan Plateau went up, and the Ganges valleys went down, and then filled with sediments in the Ganges Valley. You see that theme all over, especially in the Rocky Mountains here. Yeah, this is all Cenozoic, and this would have to be practically all post-flood. Now, in some cases, it might have started in the Cretaceous, but practically all of it is post-flood, from the flood, and it's enormous worldwide. Again, one of my main criterion of 33 I developed, Tim Clary reinforced several I had already mentioned, already developed, plus a couple more. So about 35 total. And by the way, I think I can find more if I try, but I haven't really tried for 10 years. So I've gone on to other things like how to explain the strata that we do have. That's kind of what I'm thinking of now. So
that's very powerful evidence for a higher flood boundary, Mike. I appreciate those. Absolutely. All 35 of your criteria are, and the audience can see those in detail, of course, in your articles, but also in your 2 presentations with us.
Yes, in my presentations I've already done.
And so, okay, well, great responses. I can move to question 2, Mike, if you'd like.
Okay.
And okay, so question 2, basically, again, on the flood boundary issue, an important issue as we've conveyed. In the Cenozoic is how some lower flood boundary proponents would argue, specifically in North America. They say the dominant types of sediments look very terrestrial. They have entirely terrestrial organisms with no mixtures of marine organisms with them. And so they would argue that the lack of terrestrial organisms mixed with marine organisms is good evidence for a lower flood boundary, since they would say this isn't part of the flood itself. What's a good way to respond, or what are your thoughts, Mike?
Well, I look at the 35 criterion and say there must be an answer for the flood. But I believe we need to check the data first. I've heard that argument, and it's a good argument. In fact, at the International Conference on the Creationism, it was mentioned. So since I only had about 5 hours to think about it, I thought to myself, do I know any places in the Western U.S. where there's marine fossils in the Cenozoic? And the answer is yes. Okay, off the top of my head, there's Sharktooth Hill near Bakersfield, California, where I used to live. That's middle Miocene, which is the very beginning of the late Cenozoic. Sharktooth Hill. How they all collected in that one area is a good question for future research. Like a lot of bone beds, there's hundreds of bone beds across the earth. I even have a book pretty thick on bone beds. Dinosaur bone beds are the most impressive, with thousands of individuals. So that's one area. That's in the southern San Joaquin Valley of California. Also, I showed you the Green River Formation. And this probably demonstrates why the issue of terrestrial versus marine, because the main criterion for determining whether strata is marine or terrestrial is the fossils. So if you find terrestrial fossils, it's automatically from a terrestrial environment, and vice versa for marine. But the Green River Formation, which is famous for its oil shale and its other fossils, has marine fossils in it. They're herring. And also there's a stingray. Now, since they believe it's overwhelmingly a terrestrial environment from a lake, they say these must be freshwater herring and a freshwater stingray, which is possible, but I'm not sure how probable it is. But regardless, they'd be marine fossils, but redefined as freshwater. So I'm thinking that maybe they're defining a lot of fossils they find that are marine as freshwater, like they find shark teeth in various places like Sharktooth Hill near Bakersfield, California, in spots. And of course, they would explain it. So you got to explain that away in that, from their point of view, in that sharks came up rivers and died and their teeth are in terrestrial environments. Well, that can occur. In fact, has occurred. But I don't know whether you can really use that as good evidence. But so the upshot of this, I'm thinking that they defining a lot of or some fossils as terrestrial when they really are marine. But I'll admit that the vast majority of the Cenozoic fossils are from a terrestrial environment. So that brings up further questions we can research, but I'm excuse me, but I'm for looking at the data first to really see what we have there. I'm sometimes suspicious when they talk about all these freshwater mollusks versus marine mollusks. I don't know enough about it. My biologist friend maybe tell me, is there a real difference between the two that you can tell when you find a fossil of a mollusk? Or are they generally marine and they're just found in what they think is a terrestrial environment, so they're automatically called freshwater mollusks? So I don't know, but that's a problem. Another thing. Now these are deposits and formations that I'm familiar with. That I'm mentioning. In the Palouse, I mentioned the Palouse silt. Now, the Palouse silt is about 100 feet thick, covering practically all of eastern Washington. It's very rich in that they farm on it, like the Palouse Hills of southeast Washington. But the secular scientists, you can find this in the old literature, reported, you find sponge spicules in what's called the Palouse loess. Sponges are predominantly marine organisms, even though there's claims of, and there probably are freshwater sponges like Lake Baikal in southern Siberia, but I would think it'd be very rare. And by the way, these sponge spicules are not rare occurrences. I went around with the late Dr. Harold Coffin sampling the Palouse silt, and we found sponge spicules at about 25 locations in southeast Washington, everywhere. So it's not rare, it's common. So this could be, now it's interesting how to explain this, and I've attempted it in the past, but for this purposes, it looks like a marine organism, the skeleton of a marine organism within silt. So I don't think it's a loess, which is a windblown silt, except at the very top meter or so is obviously windblown. But being 100 feet thick, I believe most of it was formed during flood runoff, probably in a low slackwater area caused by the uplift of the Cascades. And that's when it dropped the fine silt layer, silt particles with the sponge spicules. Anyway, those are 3 locations. So I'm for checking the data first to see if that's correct. I'm only familiar with North America. If you go to other continents, you might find that's not true at all. You might find a lot of marine fossils in the Cenozoic and other continents, but I don't know. But I'll give it to them that that the vast majority of them are from a terrestrial environment. And if it's from the flood, what is this telling us? The other 35 criterion would say from the flood, it seems like flood deposition was by environments. Whole environments were eroded and deposited with very few like for terrestrial environments, very few. And so the geological column goes from marine fossils up to terrestrial fossils. And this could easily be caused by vertical ecological zonation and even horizontal ecological zonation. People, creationists don't think about the horizontal, that we might have had whole different ecosystems. I'm not pronouncing it, ecosystems in one area, and you go maybe 5,000 kilometers in a different direction, you have a whole different type of ecosystem, and the flood buried them as different ecosystems. So that's kind of how I would respond. And anyway, I think that's, I didn't have any slides on that. So
No, that's good.
My answer in 5 hours.
That's very good. In 5 hours, Mike, you're a good critical thinker. There is someone in the chat that points out, and this might support what you're saying here. Maybe you have some thoughts. They say the very large Monterey Formation is marine and also in the Cenozoic.
Yes, because there's whale fossils, and it's late Cenozoic Miocene. There's whale fossils in that in the diatomaceous earth in the Monterey Formation. Yeah, that's another example. I didn't think of that. So that's the fourth example of this.
You mentioned. Oh, go ahead, Mike.
No, I'm done.
You mentioned the high point of the flood, if I remember correctly, was the KPG, with the receding phase comprising most of the tertiary. And so we'd expect basically what we see, like you were saying earlier, where you've got the receding phase after the high point of the flood. So it would look like the level or amount of intensity in terms of the catastrophism is being dialed down.
Yeah, it would probably through the Cenozoic, because it looks like the mountains rising started in the early Cenozoic and definitely concluded by the late end of the late Cenozoic, because during the Ice Age we didn't have hardly any vertical tectonics. Yeah, so, but this is exactly what you expect in the flood. It has to dial down.
Right.
So, and also the size of the formations have to decrease. But where the peak of the flood is in the geological column, I think we need to revisit that, because I believe that the Cenozoic in these mountain valleys where I live here in Southwest Montana and Wyoming and other places, lost my train of thought suddenly.
No, that's okay, Mike. I wanted to ask one more question on this issue, and then Matt, I know you got some of your own questions too. And so I was curious, because you talked about erosion in your presentation. You've also given an entire presentation here on the receding phase of the flood.
Mm-hmm.
In terms of the flood boundary debate, what about the lack of erosion at the KPG? I'm wondering where are the canyons or the erosional remnants as the waters basically run off the continents at the end of the flood. Correct me if I'm wrong, we don't really see canyons formed until relatively recently. We don't really see canyons at the Cretaceous. It's pretty much flat, if I'm not mistaken. And so...
Yes, it's true. You're right. You'd expect all kinds of features in the Mesozoic, especially in the Cretaceous, that aren't there. Oh, I know what I was going to say. Where the peak of the flood is, I think the early Cenozoic in the Rocky Mountain valleys here is early flood strata. So the peak of the flood would include the early Cenozoic mainly. Why? Because the top of the Cenozoic in the mountain valleys has been eroded down several hundred to several thousand feet. The top of it's gone. It's been eroded, and that fits with the recessional stage. And so what's left would be from the early flood, especially when you have tracks in it, tracks of live mammals, and mammals have to be, you'd expect to be dead by the peak of the flood. So the strata, and I've written about this over the years, the strata in the high valleys, mountain valleys of the Rockies here, likely is from the early flood. So in this area, the peak of the flood would be up in the early Cenozoic. But the continental shelf strata is from runoff. And that Cenozoic would be from the late flood. But then in the ocean bottom, they claim there's ice rafted debris in the early Cenozoic. Now, this has to be checked out. I'm a little suspicious. But if it's true ice rafted debris, you had to have ice sheets, the Antarctic ice sheet and even the Greenland ice sheet in the early Cenozoic. And so that would mean a lot of ocean bottom sediments are post-flood. So the Cenozoic is what I call diachronous, formed at different times in the flood, post-flood, depending on the area of the world, from the high Rocky Mountain valleys to the continental shelf to the ocean bottom sediments. And I've written about that several times, and I think I'm going to write about it again coming out with more data. So the peak of the flood was variable in different areas, is what I'm saying.
Right.
I hope you clarified something.
You did, because especially for the audience, it's not like this strict line that we can draw on the line. Right. Yeah. It's a higher or late Cenozoic flood boundary, but variable.
Yes, variable for the flood, and I believe that every location has to be examined on its own merits.
Right.
Like the Australian marsupials, which I took a good look at, and I went along with Chad Arment's view that they're post-flood, and they're dated clear down to the late Oligocene, which is the very latest part of the early Cenozoic. But when I investigated this, I found out that they've been pushing them back, the fossils back, because of their stage of evolution and primitive features from the Pleistocene, which they first dated them, down to the Pliocene, Pleistocene, Miocene, and then the top of the Oligocene, based on just stage of evolution. They had hardly any radiometric dates in these isolated areas of Australia. That's published in the Journal of Creation, by the way, I might add, about 2 years ago or 3. It might be online by now. I don't know. They publish a lot of these online after a while. But if anybody in the audience that doesn't get the Journal of Creation and the Creation Research Society Quarterly, you should get it if you want some good new research on all these topics, including biology and astronomy, of course, and other topics that will appeal to other people.
Amen. Yeah. I've got a whole bunch of magazines behind me, endless reading, great articles. So since we hold to a late Cenozoic but variable flood boundary, Mike, I'm wondering, when it comes to the North American mammal challenge to those like us who hold to a higher flood boundary, could moving the boundary slightly higher in areas of apparent fossil overlap fix some of these challenges, since it is variable? Maybe in certain spots the boundary is supposed to be a little higher, where we find the overlap in these the mammal fossils.
I think that can explain a fair amount of it. Like I did a research project, published 2 articles on terraces in the upper Wind River Valley southeast of Yellowstone Park, and I determined that the pediments and planation surfaces, which are late flood runoff features, based on that, the ash from the last eruption of the Yellowstone supervolcano, the Lava Creek B ash, was found in the pediment gravel, indicating that all those eruptions were late in the flood and not post-flood, which had been a question I had for 25 years. But then as you go into the Midwest, where the Lava Creek B ash is located, it used to be it's a marker horizon. They dated about 640,000 years, something like that. And so that's how they date some of their mammals. But a lot of that covers up a lot of mammal areas. So I based that and other things that the Cenozoic mammals in the upper Midwest, in the southern and central upper plains like Nebraska, eastern Colorado, South Dakota, in there, that these mammals are from the flood. So you analyze them in deep cuts. There's a lot of them in the walls of those valleys. And if you interpolate between these, there's probably millions of mammal fossils buried in the top strata of the high plains, which is eroded down to this level, I might add. So the boundary there would cover up the flood post-flood boundary would probably be in the mid-Pleistocene. Pleistocene is no magic value for the Ice Age, by the way. There's strata a couple thousand meters thick in some basins that is labeled Pleistocene. So that's, to me, obviously not post-flood, but that's just a slot. So in some areas, the boundary could be in the early to mid Pleistocene, and that would explain a lot of the mammals below that as being from the flood, and not putting a boundary down at the Pliocene Pleistocene, where then you do have a lot of boundary crossing mammals in the Midwest and the plains. So I think I could solve that, but I need to write more about it and get into the pronghorn antelope example that Marcus Ross brings up, and he brought up again in the forum at the International Conference on Creationism. So I need to visit that more. I've written 4 articles on it in the journal Creation already, trying to get into this, and I'm going to do it more this winter. But if I get around to it, I got so many projects this winter. But anyway, that's how you're right. By having a flexible boundary, we can explain some of these so-called boundary crossing genera.
Right. Well, that's a great response. Actually, great responses all around, Mike, to those questions. I could talk to you about flood boundaries all day. And so what I'll do, though, Matt, I know you had a couple of your own questions, and then we're going to get a few of these audience questions in, because we do want to wrap things up by 7 your time, Mike. So again, excellent responses to those questions and challenges. Matt, brother, a couple of your own questions that you wanted to ask.
Sure. One of them would be, have you ever looked into the Ashley phosphate beds of South Carolina, or any of the beds that run all the way from Florida to Canada? Because those were really popular for a while, where we had found things like dinosaur with man. So have you?
Yeah, I was thinking of that as another example of marine and terrestrial fossils mixed, but I don't know enough about it to say much about it. But I didn't know it went up to Canada. I thought it went from Florida up to South Carolina, the eastern parts. But like I said, I don't know enough about it to even state anything. So okay. I'm just going to beg off. Right. It needs to be researched. It looks like a great research project for someone.
For sure. I've only ever found 2 studies where people have gone there, and that was it. So,
wow.
All right. Here's another one for you regarding ice layers and ice cores. How many layers can we actually visualize and count on our own before we just can't do it anymore? And how do they assume that there's hundreds of millions of years by counting these layers?
Well, they claim that you can count layers down the Greenland ice sheet in one core down to 110,000 years, but it's near the bottom. So you only have a little over 100,000 years for the whole Greenland ice sheet. That's far cry from the millions of years. But of course, they think it's all compressed, and each ice age is maybe 5 centimeters, remaining 5 centimeters thick because of the compression. On Antarctica, the most amount of age they have is only 800,000 in the Dome Sea core, ice core. And that's near the bottom of that. So the Antarctic ice sheet obviously isn't millions of years old, but they have ways of explaining this, is that compression makes them disappear at the bottom. They thin out, and as you compress the top, they stretch out on the sides. So they have explanations, but you certainly don't see on the basic evidence that there's that millions of years in those ice sheets. But there's explanations for the annual layers. You don't find annual layers on the high elevation East Antarctic ice sheet. You find them in the low altitudes and in the West Antarctic ice sheet. You find them mainly in Greenland, but they're nice annual layers in maybe about 10 to 15 variables at the top. At the top of the Greenland ice sheet, you get about that much ice a year. And that's thick enough to show annual layers. They show up nice, but as more snow piles on, those annual layers are compressed down deeper, deeper, deeper. And by the time you get down to the bottom, they're about the thickness of a dime, I might add. That's if it's been steady state for millions of years, as they claim. But the annual layers that show up really nice at the top of these ice cores, not only they're compressed, they thin out, but diffusion mixes them some. They don't show up particularly well midway down in the ice cores, especially at the bottom. The oxygen isotope ratio, which is which is generally, well, I should say roughly proportional to temperature, has nice annual layers at the top. But in this GIFT 2 core, the core that they showed the annual layers, it gave out in 300 years. It totally gave out. There's no reason for that. So it's showing you that these annual layers are kind of starting to get fuzzy, only the short distance down. So they go to other ways to count annual layers. One of the main area is dust layers, especially the bottom half of this GIFT 2 core, which is drilled at the top of the Greenland ice sheet. It's about 2 miles deep, ice core. And the problem is that they find a lot of dust layers, way too many for annual layers down in there. So there's a lot of confusion down there, but they wing it. And to show you that there's preconceived ideas that go into all this stuff. The annual layers don't work out too well when you get at least halfway down. I should say at most halfway down. And the top half is only about a couple thousand years old. So it's the bottom half that's most of your supposed time. And they're not very good for annual layers down deeper in there. So they depend on other variables to date the ice sheet. For instance, the Milankovitch hypothesis, or the astronomical theory of the Ice Age, which we can do a whole talk on. The cycle of each ice age, assuming this theory, which is a very weak theory, I might add, it changes the radiation balance in the Earth only slightly. It oscillates every 100,000 years. So they think each ice age for the last million years is 100,000 years. That's the main dating method for the Antarctic ice sheet. But it also forced the annual layer counting of the Greenland ice sheet. And this is plain as day, because when they got down to near the bottom of this core, they only got 80,000 years. And it did not agree with the Milankovitch or astronomical theory. So they said, redate it. So they redated the bottom 500 meters with a finer instrument that formed more annual layers. It's called the LLS instrument. It's a laser light stratus or something like that. And so the original counting down to 80,000 years was with a resolution of 8 millimeters. So they made the resolution 1 millimeter, and guess what? They found 25,000 more annual layers in the bottom 500 meters to make it 110,000 years at the bottom, exactly what they expected by the Milankovitch theory. And this is plain as day in the journal Geophysical Research, and I pointed this out widely in my material. So there's a lot of circular reasoning going into this dating. To summarize, you can't get annual layers more than a couple thousand years at the most. And beyond that, you're assuming the Milankovitch theory. And so theory works in and dates the rest of it, whether they're annual layers or not. So that's a kind of a long explanation. You can read all about it in the Frozen Record from the Institute of Creation Research, which you can still buy. It's still in print.
Awesome. Thanks.
Okay. Great questions, Matt. Excellent responses as always, Mike. So here's a question. So I've seen this argument employed for years as one of the best so-called objections to the global flood model. So
Yes.
The question is the Green River Formation. And before I continue reading it all to the audience, Mike, you, me, and George Bond, probably about a year ago, did a somewhere between 2 and 3 hour show on the Green River Formation.
Yes.
So I highly recommend people check that out. So the question is, the Green River Formation covers tens of thousands of square miles.
True.
With at least one location comprising 20 million varves. Can the young Earth creation model account for these varves in a short period of time?
Well, first of all, I don't believe I never heard that 20 million varves. I've heard 6 or 7 million varves. So I think that's an exaggeration, or I haven't run into it, or unless they got newer data. And I try to keep up with that topic in the 50 journals I try to keep up with secular science. Varves are automatically a 1 year period. And there are true varves on the surface of the earth in lakes today. But the question is, are these rhythmites, or technically rhythmites, which is a repeating couplet of 2 or more sublayers or subcouplets? Are these true varves? First of all, they're only a millimeter, or a fraction of a millimeter thick. So if they are 1 year accumulation, why do we get all these fossils in there? Some of them are pretty good sized fossils in the so-called varves. Well, obviously, there's big problems with them being varves. They're rhythmites. And by the way, there's a lot of rhythmites across the earth and a lot of formations of all ages, I might add. And I would say we do not have a good explanation for all this, except that we can, I think, pretty conclusively conclude they're not 1 year accumulations for each couplet. How would we explain them? Well, I think one possibility is that during the flood, I believe the Green River formations from the flood, and we had a lot of internal waves. Internal waves are waves on any surface of discontinuity, density, like different salt layers, different temperatures. You can have waves. And these waves can erode and deposit in a rhythmic pattern. And today you could see these internal waves through the ocean. They're detecting them. And during the flood, with so much chaos and vertical tectonics, you'd probably have millions and millions of these internal waves. And it's possible to connect internal waves with rhythmic deposition. So that's one possibility I've published. It's in the Journal of Creation as a possibility to explain thick rhythmites. But so that's a topic of research. We need to do more research on that topic. But a good question. I get it all the time, that question. Okay.
Great answer. If there wasn't... Okay, here we go. I hope I'm coming in okay. My internet seems to be a little low currently, but as long as you can hear me coming through, I think we're good. Okay, so next question comes in from CC. Explain the massive uplift
see
of the
it.
Colorado Plateau, which happens in conjunction with river downcutting over millions of years.
River downcutting is an assumption, a secular assumption. But if it uplifted rapidly during the flood, all these river downcuttings and the formation of canyons and water gap can occur rapidly, just like the rapid formation of water gaps I showed. The same thing can be applied to the Grand Canyon, for instance. The Grand Canyon is just another water gap of the thousands across the earth. It's the longest, but definitely not the deepest, not even in North America. The deepest water gap is Hell's Canyon, 50 miles long, up to 8,000 feet deep on the Idaho side. Yeah, I believe it all uplifted late in the flood, the Colorado Plateau. And the Colorado Plateau, as it uplifted, was rode at an average of 2,500 to 5,000 meters. This is from a journal article by Schmidt in the journal Earth Processes and Landforms. It's a geomorphological journal. And so, yeah, as everything came up, you had a massive erosion. But why it uplifted, we really don't know. And neither do they. Neither do the secular scientists. In fact, Ollier and Payne, in that book On the Origin of Mountains, listed 20 theories on how you get vertical uplift. And they said in that we can't prove any one of them. So I think some of them we can use, like heating from below will cause expansion and uplift. Compression, they believe the Rocky Mountains uplifts are formed by horizontal compression. That's probably correct, even though it looks like it's more vertical tectonics. But anyway, that needs to be researched. But anyway, I can't explain the details of why things uplifted and why ocean basins sank and valleys adjacent to a lot of mountain ranges sank and filled up with sediments during that. And the top got eroded off after they filled up. But I don't believe it was over millions of years, but it's a flood signature. And the flood is the great time cruncher, I might add. What appears when we think of present day processes would take millions of years, which would be true, it would take millions of years. The flood greatly accelerates all these processes.
Right.
The origin of coal can form rapidly, oil can form rapidly, ice ages after the flood form rapidly. Lots of things form rapidly, including uplift, and sedimentation occurs rapidly. So the flood is a great time cruncher is what I would say to summarize the answer to that question.
Well said. It's a simple statement, but it's true in light of what you're saying. You know, a lot of these features of the earth are due to a process rather than time. And if those processes were accelerated during the flood, Mike, do you believe a lot of the heat and energy produced during the flood is what could have got those plates moving faster in the first place?
You're getting into plate tectonics and catastrophic plate tectonics.
Yeah.
I don't want to. I can get off on this topic for a whole hour, and I don't spend a lot of time dealing with it because I have a huge research agenda that has nothing to do with these topics. But I slowly look into this, and so. But what I like to do is look at the observations that draw the conclusion of plates moving. You know, when I look at these data sets, I find glitches in them, like subduction zones. And so things don't seem to be exactly like they said, but yet there's evidence for it. And I'm looking at some of it right now that seems to be more positive for catastrophic plate tectonics. So what I'm saying is that after 40 years, I still haven't looked at enough research of the assumptions and data that goes into the conclusions and sorted out the difficulties to make a decision, yay or nay, for that to even answer that question. If I do come to believe in catastrophic plate tectonics, which is a possibility down the road, there's still a lot of glitches in that a model that need to be worked out.
Right.
I don't think it's the simple stuff that I read from the creationists on that topic. I think it's a lot more complications. We need a lot more in-depth research. We especially need to go into the data sets. People just simply say, well, the fossils can be matched across the Atlantic. Well, that's a simplification, because you can match the fossils with interior US also, like conodonts. One secular researcher who published an article favoring plate tectonics by the same or similar conodonts, which are early Paleozoic, I think they're teeth of vertebrates, are matched across the Atlantic. But then she discovered the same thing in Nevada, and so that kind of nullified her idea of being able to match these fossils across the Atlantic. So the original idea is a simplification, but it may be true. What I'm trying to say is people accept this, need to look thoroughly at this data, the assumptions, before we make conclusions. So I'm slow at working my way through that, but I'm finding more positive evidence for the splitting of the Atlantic. But I'll tell you, we have a lot more to do dealing with that whole paradigm of catastrophic plate tectonics.
The importance.
Good start.
Yeah. And it's the importance of, as you like to point out, Mike, multiple working hypotheses.
Yes. I think that meteorite impacts or comet impacts, I think it doesn't matter, they'll do the same thing, are a big factor that's being neglected by the CPT people that I've worked on a lot. And I'm going to publish stuff on my website on this coming up as soon as I revamp it. Thousands of pages of information I have ready to go, but I'm going to embellish more on it. These would be a factor in catastrophic plate tectonics, or it could be a standalone model. But it can be used to account for a number of mysteries in the earth science that are difficult for catastrophic plate tectonics to explain, like what's called large igneous provinces, where you have huge basalt flows over huge areas. The Columbia River basalts, I showed you some in eastern Washington, are one of the smallest basalt flows, but they cover 200 square kilometers up to 4 kilometers deep. Some of them are 10 times that size, like in the Purana area of north central Siberia, the Deccan traps in India. Where does all this basalt come from? It obviously comes from the mantle, but what caused the melting? Well, it's possible, and some secular scientists think that impacts could cause the melting, sort of like the salt in the large craters on the near side of the moon formed kind of like that. So it can explain a lot of things that catastrophic plate tectonics alone can't explain. So I think if we're looking at these models, we need to consider impacts in catastrophic plate tectonics if catastrophic plate tectonics turns out to be true, which it may well be. I'm still working on that, and I'm getting more positive evidence that nobody's even heard of, that it could be true. So I'm still working my way through it. So I can't answer that question directly. Sorry.
No, that's okay. Well said. Well said. I appreciate your responses, ideas, and thoughts, Mike. We appreciate all the research you're doing. Matt, I'll put the next question up on screen, brother, for you to read and present to Mike.
Sure. Does fresh water ice age flow drastically change the apparent salinity of the otherwise marine deposit sediments?
Well, the ice age would be post-flood, and marine deposit sediments would generally be from the flood. So I'm not sure how to answer that or what the question is meaning. A lot of people have questions about the fresh water versus salt water during the flood. And one thing, fresh water will float over salt water for a while until it mixes because of the freshwater has a lower density because of no salt. So there's not much marine deposition going on today, I might add. We see sometimes a turbidity current go down the continental slope onto the deep sea. That's about the only marine sedimentation I know of. And we have delta deposits. So there's not a lot of marine sediments being formed in the marine environment compared to what's out there right now that formed during the flood. So I don't know how to connect the post-flood ice age with that. So that's not sure of the question. I'm not sure the guy who asked it stated it correctly either. So,
Mike, I've got questions in the audience on the Grand Canyon. What I'm going to do is kind of sum them all up into my own question that I think will cover them all. Before I do, the Grand Canyon is another topic we covered for probably between 2 to 3 hours about a year ago. Mike, you gave a fantastic presentation. So
yeah.
definitely people looking for an all-encompassing show on that topic, check the description box. So the question is, was the Grand Canyon formed after the flood, or is the Grand Canyon being formed by receding floodwaters channelizing and carving out the Grand Canyon?
Well, that was an hour talk or hour and a half talk with a lot of questions. But to make it a 1 minute answer, the Grand Canyon is a water gap. And there's thousands of water gaps across the earth. Dozens of them in the western US, some very deep, even deeper than the Grand Canyon, like Hell's Canyon. So the Grand Canyon would logically be placed how other water gaps are formed late in the flood by channelized erosion. And the opposite idea of their post-flood lakes that breached has numerous problems, which I have published. I'm going down in early October to look at some new evidence claimed for the dam breach hypothesis. In early October field trip. And so I'll check out future claims, but I'll probably write another article about it. But I think the evidence overwhelmingly indicates that it's a post-flood water gap formed like other water gaps from the top down. Because one problem is it's the first plateau that the Grand Canyon passes through is the Kaibab Plateau, which in a north-south direction is bowed up like this. But Grand Canyon isn't formed starting at low points, like to the north. The lowest point is 5,700 feet above sea level. It starts at intermediate altitudes, 7,200 feet to 8,200 feet on the south and north rim, because it's carved on the south-facing slope of this Kaibab upwarp. So how did that happen? That's a very big problem for the dam breach hypothesis. So they got to postulate this Kaibab plateau oscillating or whatever to try to account for it flooding over that. And not only that, once it passes the Kaibab plateau, the water should have gone down the topographic slope, which would be to the west. But instead, it goes northwest at the same altitude along the southwest Kaibab plateau. That's where the canyon's carved. It doesn't go down any topographic slope, it stays parallel to the topography. So those are some pretty powerful arguments, among others, about the dam breach hypothesis, which would be the alternative post-flood idea, which I think there's lots of evidence against. So I have a whole book on it called The Grand Origin of Grand Canyon. You can get from the Creation Research Society. So if people want to know more details, and also have a 5-part article published about 10 years ago in the Creation Research Society Quarterly, and one recently about 2 years ago in the Creation Research Society Quarterly. And so I'll check out this new evidence and probably write another article. So to me, it's just logical. It's just like the thousands of other water gaps across the earth formed by late flood channelized erosion. It fits in like a T to that time frame.
So what are your overall thoughts then on Lake Hopi? Do you think there's some evidence that it may have existed? Because I've heard recently that there's a lot of evidence that this lake was extensive and may have even held a lot of deep water, basically enough to cover the Grand Canyon.
Yes, Lake Hopi is one of 2 or 3 lakes. The other 2 or 3 are to the north or northeast of Grand Canyon.
Right.
Hopi Lake is supposedly fills up the Little Colorado River Valley, southeast of Grand Canyon, and to be a monster-sized lake. I forget the volume and the area of it, but it's a huge amount of water. And so I pointed out that you don't see shorelines on it, even though there's a claim for shorelines made at the International Conference on Creationism, but they don't really look like shorelines to me. But I need to check them out before I say anything more. But shorelines are nice, even cuts like that. Just strand lines. These others kind of wave. There's some kind of oscillation, but I don't know what they are, how to explain them otherwise. But regardless, there should be shorelines all over that. Just like with you go across the mountains from where those lakes occurred in the Great Basin, there's shorelines all over the place with the lakes that occurred during the Ice Age. Some of them huge. And I showed you shorelines from Glacial Lake Missoula. They're all over where the lake occurred. And they're in hard and soft rocks the same. So you can't say they weren't formed because the rocks were too soft and they eroded afterwards. Because soft rocks still show the shorelines of Glacial Lake Missoula. They haven't eroded out yet. So it should have shoreline. And not only that, Glacial Lake Missoula, which is up to 2,000 feet deep, has bottom sediments, Some of it eroded out, but a lot of it didn't get eroded out. And bottom sediments, to form those, they're formed by river deltas usually coming in, and then they slough down by mass flow and fill up the deepest parts of the lake. So you should have a couple hundred feet of lake bottom sediments around Cameron, Arizona, and that whole valley, but you don't find any bottom sediments whatsoever. It's claimed that the Bitahoche Formation is bottom sediments, but there's problems with that, especially since they go up to about 1,000 feet higher than the top of the lake level is supposed to be. And there's a lot of things with that. That's another area I need to investigate what that all means. It fits in somehow, but I don't think they're lake bottom sediments, especially since they're northeast of the lake. You should find them more in the western part, and the bottom you don't. And you can't get rid of them from erosion during the dam breach because the water went through a very narrow slot canyon when it exited Hopi Lake. I've shown pictures of this. It's probably several hundred meters wide. It's very narrow and deep, maybe half a mile deep. And the water would be rushing through there, but it's so narrow that it's not going to erode the sediments other places where the currents would be slower in that big wide lake. So I consider these pretty powerful evidence against the dam breach theory. But anyway, I was going to only answer that in a minute. I actually have to go in 13 minutes because I have to mow the lawn before it gets dark around here.
Yes, well, firstly, you're an encyclopedia of information, Mike. I always look forward to our shows together because I learn so much, and I personally appreciate the thorough answers. So since we only got a few minutes left together, we want to get you out of here by 7, Mike. I am going to pick the 2 most pertinent questions maybe, and we always get unlimited questions from the audience. I'm going to save the rest of them for hopefully another future show with you, Mike. So
Maybe
this comes
a question and answer session down the road.
Yes, actually, I think that'd be a good idea. Is just do a nothing but question and answer show. Get the audience to maybe even send in questions ahead of time. So this comes in from Paul Price. Paul's written many excellent articles for creation.com as well.
Okay.
And so he's asking, I'd like to know if Mike Oard is aware of any other examples of unpermineralized dinosaur bone besides the hadrosaurs in Alaska from Maury A.L.
First of all, I hadn't heard of that example, but we find unpermineralized dinosaur fossils in Montana. For instance, there was a T-Rex found that used to be in the Museum of the Rockies here, which is a great dinosaur museum full of evolutionary stuff, I might add. That was unpermineralized. It's called the Wanko T-Rex. And they even had kiosks about where they actually found red blood cells and right next to it, but it's gone. The Smithsonian supposedly has it, but I wonder if they show it. But it was up in the Museum of the Rockies for, I don't know, 5 or 10 years before it disappeared. And I think if you look at the Creation Research Society, the iDino project, they have quite a few examples. And ICR has a whole list of unpermineralized fossils, some dinosaurs and even some older than that, than dinosaurs. So there's getting to be quite a few of them around. But I hadn't heard of this hadrosaurs in Alaska one, but I don't keep up with that topic a lot. I just know about it. I've written a little about it, but that's about all I can say on that one.
Very good, Mike. Okay, so next one comes in from Jackson Rowe. Jackson's asking, why are 1,500 species of conodont teeth found in predictable layers from late Cambrian to Triassic? What flood model can explain this?
Well, the first thing I would say is that I'd want to verify that a deduction of 150 species of conodonts, first of all, they have way too many species for the same or similar feature. So they're probably a lot less species.
Right.
They found this with dinosaurs, for instance. And besides, the Bible uses the word kind. And I'd say from the baraminology people that the average kind's probably at the family level, the average, that is. So this might only be a couple hundred species. I'm based on that idea. And are they really in predictable layers? That I'd really want to verify. I know they're used as index fossils for some formations, mostly in the lower Paleozoic. I hadn't heard of anything about the upper Paleozoic or the Triassic in the early Mesozoic. But I'd verify the data before I would say anything more. But I will add one thing on vertical fossil order. There is a vertical fossil order. And like I said before, I think it can be explained by the erosion and deposition of various ecosystems from various areas. And there's a number of things to explain. And if we use the geological column as a general vertical scheme of deposition in the flood, for instance, we have dinosaurs, mainly in the Mesozoic. But I might add there's been Cenozoic examples that get redated or something like that end up back in the Mesozoic. There's a little bit of circular reasoning in dating the last dinosaur. But there's also some other intriguing things, like angiosperms don't show up until the early Cretaceous. Why aren't they found in other places? And diatoms. Now, this one's especially strange. Diatoms are ubiquitous. They're everywhere, fresh water, salt water, but they don't show up in the fossil record until about the Cretaceous. Why? Like I said, I think there are different environments, both vertically and horizontally, that were deposited that would generally explain that, but that's just a general explanation. We need more details on, for instance, where the sediments come from in the first place. I have some ideas, but at this point, I'd better not speculate. So, yeah, Good question. I know your general ideas, but I'd check the data on this one first.
So when we look to these communities you're talking about, or these ecosystems, let's say the Cambrian community, the Ordovician community, the Mississippian community, these are communities basically living at the same time, but living in different places rather than communities evolving over time, like the evolutionists would say.
Yes, both vertically and horizontally. Vertically, and then you go from marine to terrestrial. So you'd expect in a giant flood the marine organisms to be deposited first. So, but there's, I think, a lot of horizontal zonation that isn't accounted for. That can account for some of these oddball things like diatoms. Possibly you had diatoms pre-flood only in certain areas that didn't be deposited until, say, midway in the flood. That's kind of what an idea I have on that, but it's just an idea, a speculation. I admit it. So we need more research.
Mike, very good. What I'm going to do is save the rest of the questions for what I think would be a great question and answer show in the future with you. And some in the chat say they like that idea. So that's something we'll discuss.
Okay.
As always, Mike, time flies by with you, brother. Great answers to some excellent questions and challenges. And also, as usual, fantastic presentation. I look forward to digging into it more later on. So, Mike, let's hand it to you in case you had any final words or final thoughts before we wrap things up.
Well, I would say we have the big picture of the sedimentary rocks hands down as evidence for the flood, because they're a lot of times found over wide areas like the Tepete sandstone and its equivalents over half of North America. Then the next sediment are present one after another in quick succession with little or no erosion. It doesn't show millions of years of slow processes. Slow processes like we see today, no, these are wide formations over huge areas and one layer laid rapidly on another. So that's the big picture. And that can be explained by Noah's flood, depositing sediments over a huge area, one on top of another with little or no erosion at the interfaces. So that's the big picture. But details, lots of details. And that's why I keep telling people I have 500 years worth of research and writing left to go. We have a lot of things to answer, no doubt about it. And the secular scientists are good at bringing those things up. But, when I analyze a challenge, by the way, the Lord has led me to analyze challenges, not necessarily to challenge evolution, which is rather easy. Don't have to know a lot about it. You find out that evolution has numerous problems, like that book, Evolution's Achilles' Heels, goes through 8 fatal problems.
Great.
He's led me to answer challenges. And so, but when I look at a challenge, I first of all find it's a challenge to uniformitarian scientists also. They're challenged on these, like ice ages, which I've studied for 50 years, or the ice age. Experts in the ice age will say we can't explain it, and they have over 60 theories. But I believe we have a great explanation from after the flood. I probably have a talk on this on Standing for Truth already. But like I said, they're challenged. They can't explain it. And this is what I commonly find when I examine these challenges. So I'd like to leave you with that they're challenged, we're challenged, but we have the big picture.
Excellent final words, Mike. And I look forward to a future Q&A for you, because I can tell you we're going to have endless audience questions, and then also unlimited questions from myself and Matt. So, and that brings me to Matt. Thank you for co-hosting, brother. As we wrap this up, any quick final words?
Absolutely. No, that was good. That was great. People loved it too. So have to do it again.
Absolutely.
Okay, and I'll love to answer questions.
Yes, and you're great at it. So, Mike, we're going to chat, and then hopefully we'll schedule a couple hour audience Q&A in the near future. So, Mike, God bless you. You enjoy the rest of your night. Matt, again, thanks for co-hosting, and to the audience, thanks so much for tuning in. I appreciate how engaged you all are in this important topic. Share this content around because the truth is so incredibly important. God bless
Yes.
all. Standing for Truth is out.